Hi everyone, welcome to this worked example looking at percentage yields calculations. Percentage yield is an important concept in chemistry because it helps us to work out how much of a product are we going to get compared to how much we theoretically could get if all the reactants turned into product. Now, there's some reasons why not all the reactants turn into product. For example, it could be a reversible reaction, or it might be difficult to separate the reactants out, the products out from each other, or the products from the reactants. So it's useful for chemists in all sorts of contexts to work out the percentage yield, comparing the theoretical yield to the actual yield. So let's look at the information that's given in this example question here. So we're told we're going to calculate the percentage yield, of tungsten, that is our product, our desired product, in the following reaction, where 565 grams of tungsten oxide produces 385 grams of tungsten. Now, as is normal for the higher paper, a balanced equation is given for you. So from a balanced equation, we can work out the mole ratio. And that tells us how many moles of each reactant react together and how many moles of each product are formed. Now, in this particular example, we are only interested in the tungsten, which we have 1 mole of, the tungsten oxide and the tungsten. We've got 1 mole of each thing. So our next step is to work out the gram formula masses of these. So let's start with the tungsten. Well, the relative atomic mass of tungsten is 183.8 grams. And for tungsten oxide, we've got 3 times 16, which is 48, plus the tungsten 183.8. So add those together and we get 231.8 grams. That's how much 1 mole would weigh. So in theory, if we started off with 1 whole mole of tungsten oxide, that would be 231.8 grams. So now we're just going to do the gram formula masses of the substances that we know about. And that would yield 183.8 grams. So this statement here tells us that if we had 231.8 grams, we would get 183.8 grams. So now we need to say, well, we didn't start with 231.8 grams. We started with this mass, 565 grams, which is a bigger number. So we're going to expect a bigger mass of tungsten to be produced. So we actually started with 565 grams. What mass would we get? i.e., what is the theoretical yield? We're just going to backtrack though and say, well, it's a bit tricky to go from one number to the other, especially for people who struggle a wee bit with calculation. So we're going to actually say, well, what would 1 gram give us? To get from 231.8 down to 1, we divide by 231.8, Any number divided by itself is 1. So we do the same to the other side. So 183.8 divided by 231.8 is roughly 0.8, so it's 0.7929 and so on grams, So that's what 1 gram would give us. We, though, started with, what's our theoretical yield? Sorry, that's not our theoretical yield, that's our starting mass. We started with 565 grams. So that's going to give us, to get from 1 to 565, we times by 565, so we do the same to the other side. So 0.7929 multiplied by 565, and the answer we get is about 448 grams. Now this number here that we've just calculated is our theoretical yield. It's the maximum possible mass of product based on a certain starting mass of reactant. Now, we need to look at our percentage yield equation. So percentage yield is equal to the actual yield divided by the theoretical yield multiplied by 100. So let's keep that to the side there. And now let's insert the numbers that we have. So our actual yield is here. This is our actual yield. And we're going to divide that. So 385 divided by 448 multiplied by 100. Pop those numbers in your calculator and you get 85.9%. And that is our final answer. Okay, so what we've done there, just to recap on it, we looked at the mole ratio in the question. It was a 1-to-1 ratio, so we could just simply substitute in the formula masses of the reactant and the product that we were concerned about. Then we worked out what 1 mole would give, then we scaled it up or down depending on the question, but here we scaled it up to 565 grams and we got our theoretical yield of our product. Then we popped that number into our percentage yield calculation and got our final answer. Okay, so here's a second example of a percentage yield calculation. Let's look at what this one is asking. So it's saying calculate the percentage yield of ethene in the following reaction, where 28 grams of decane produces 3.3 grams of ethane. And we have a balanced equation. Okay, so again, looking at the mole ratio, 1 mole of decane would produce 1 mole of ethene. So let's think about the gram formula masses then. 1 mole of decane, C10H22, has a gram formula mass of 142. You can calculate that yourself to check. And then 1 mole of ethene, C2H4, has a gram formula mass of 28, okay? So, inserting the gram formula masses, because it's a 1-to-1 ratio, then 142 grams would give 28 grams, okay? We didn't start with 142 though, we started with 28. Okay, now in the last example we went to the 1 gram, but here we'll just skip that step because to go from 142 to 28 we divide by 142 and then we multiply by 28. So we do the same to the other side. So 28 divided by 142 multiplied by 28. And the answer we get is 5.5 grams. Okay, so we use our same calculation. Percentage yield is equal to the actual yield divided by the theoretical yield multiplied by 100. So let's pop in our numbers. So our actual yield from the question was 3.3. So actual yield divided by theoretical yield in this case would be 3.3 divided by 5.5. Don't even need a calculator for this. Is 60%. So that is our final answer. Okay, so here's a question on atom economy. Atom economy is all about how much of the total mass of reactants goes towards making our desired product. Okay, so here's a question. Titanium can be extracted from titanium 4 chloride as follows, and we've got our balanced equation. What is the atom economy for forming titanium in this way? So, similar to the percentage yield problem, we need to look at the gram formula masses. So we need to work out the total mass of the reactants. Okay, so we've got titanium chloride, and that has a total mass of 189.9 grams per mole. Okay, now that reacts with 4 moles of sodium, and each sodium atom has a relative atomic mass of 23, so 23 times 4 is 92. Okay, so the total mass of reactants then is 281.9 grams. That's the total mass of reactants. Then we've got the mass of desired product. Now, in this example, the desired product is titanium, and we have 1 mole from our balanced equation. So the titanium is 47.6 titanium is 47.9 grams. Okay, so our balanced equation is, so from our balanced equation, the mole ratio is that 1 mole of titanium chloride reacts with 4 moles of sodium to give 1 mole of titanium. So if we insert then, to work out our percentage atom economy, we've got to do the mass of the desired product divided by the total mass of reactants. So that is 47.9 grams divided by 281.9 grams, and that comes out as 17%. Okay? So that's what atom economy is going to look like. Now, just for completeness, the total mass on this side is 281.9. The total mass on this side is also 281.9. Oh, excuse me, I put the decimal point in the wrong place there. 281.9 grams. So depending on the atom economy question that you get asked, it might be simpler to add up the reactants or to add up the products. Either way, you get the same total mass if you've taken into account the mole ratio. Okay, our atom economy example 2. Calculate the atom economy for the formation of nitrobenzene. We've got the formula here. So this is the nitrobenzene here. This here is actually benzene. And we've got nitric acid and water. Okay, so we're going to take the mass of nitrobenzene, which is 123 grams, and we're going to add that to the total mass of the benzene and the nitric acid. So the benzene is 78 grams and the nitric acid is 63 grams. So in total, that is 141 grams. Okay, so you can see what we're about to do. We are going to take this number here. This is our mass of desired product, and this is the total mass of reactants. So we're going to do 123 divided by 141 times 100, and that comes out as 87.2%. That is our final answer for the atom economy of nitrobenzene. Okay, here's our first example of an excess and limiting question. Okay, in the standard higher papers, you are given a question on excess that's phrased as prove by calculation or show by calculation that whichever reactant is the limiting reactant. Okay, if you look further back in past papers or in other examples, sometimes it asks which is limiting, which is in excess, or prove which is limiting, which is in excess. Okay, in this question here, it says at high temperatures, sulfur combines with iron to form iron sulfide, and we've got our balanced equation here. In one experiment, we've got a mass of iron and a mass of sulfur that react together. Show by experiment? That's not right. Should be show by calculation which reactant is in excess. Okay. So our balanced equation is given. So I'll just write it down here for a bit more space. So iron plus sulfur makes iron sulfide, and the mole ratio of the reactants is 1:1. How many moles of iron do we have? Okay, so number of moles is mass divided by the gram formula mass. So the mass from the question of iron is 7.6 grams, and the gram formula mass of iron is 55.8. So the number of moles of iron we have available is 0.136 approximately. What about the number of moles of sulfur then? Well, it's calculated in the same way, mass over gram formula mass. From the question, the mass is 8.7 grams, and the gram formula mass from your data book is 32.1. So we actually have 0.27 moles of sulfur available. So this is what we have available. Okay. What the mole ratio tells us is what would be required. So if we had 1 mole, we would require 1 mole. If we had 0.136 0.136 moles, which we actually have, it would require 0.136 moles of sulfur. Okay? Now, we actually have 0.27 moles. Okay, so if we just compare these two numbers, okay, this is the number of moles that we have available, and this is the number of moles of sulfur that are required. And we'll see that the number of moles that we have available is greater than what's required. So that means sulfur is in excess, okay, because 0.27 moles are available, but only 0.136 moles are required. Okay, for our final example here, we are looking at a reaction chamber where we have 81 grams of aluminium reacting with 5.3 moles of chlorine gas. Now, sometimes for excess and limiting questions, you're given two masses. Sometimes you're given mass and then information about concentration and volume. Sometimes you're given number of moles. It depends. You expect to go between them. If you're given, you can always do it by working out number of moles. Sometimes if you're given only masses, then you can just do proportion. But in this one, because I've been given a mass here and a number of moles here, then I have to calculate this in terms of number of moles. That's going to be my simplest way forward. Okay, so show by calculation that aluminium is the limiting reactant. So first thing to notice about this example is that I've got a mole ratio of 2 to 3. Okay, I've got a mole ratio of 2 to 3. 2 moles of aluminium reacts with 3 moles of chlorine gas. Okay, so how many moles of aluminium do I have? Well, I've got the mass over the gram formula mass. The mass from the question is 81. Gram formula mass is 27. So I have 3 moles available. Now, 2 moles of aluminium reacts with 3 moles of chlorine. I've got 3 moles. So how many moles of chlorine would I need? Well, I look at that proportion. So 2 to 3 is equivalent to 3 to 4.5. Okay. How did we do that? Well, to get from 2 to 3, I divide by 2 and times by 3. So do the same to the other side. Okay. So that is 4.5. It's just 9 on the top divided by 2. Okay, so 4.5 moles is what's required. This is what I have that's required. And this is what is available. Okay, and you can see that the number of moles of chlorine that I have available is more than what's required. So chlorine is in excess. Okay, all of the aluminium is used up. It is limiting. Okay, so the aluminium in this question is the limiting reactant and the chlorine is what's in excess. All 81 grams of the aluminium is used up, but only 4.5 moles of the chlorine gas is needed, not all 5.3 moles, which is available.